consume more line, and it's easier to talk for me if I see faces. So if anybody wants to show their faces, I'm happy to, of course, as you prefer, as you wish. Let me share my screen in the meanwhile. Share, here it is. So that's my topic, quantum gravity. And I assume that's not what you're doing. So this will be very introductory, quite basics. I'm going to tell you what is my opinion on where we are about this problem. And I'm going to do three things. So this will be in three parts. First, I will be talk about data experiments, nature telling us something, recent relevant experimental empirical inputs for quantum gravity. And this is, I start from here, even if I'm theoretician and not really what I usually do mostly, because quantum gravity is sometimes seen from the outside as something which has very little so far connections with what we measure in nature, and I want to sort of show that's not the case. And in fact, that a lot of recent things that we've learned from nature are enormously relevant for the theory. Then I will go into the approach to quantum gravity which I worked and which I like the best, and which I think that is more promising and more interesting, which is loop quantum gravity. And I'll tell you what is the theory and what one does with the theory, what it says. And then in the last part, which will be short, but I think perhaps most fun and most interesting, I will tell you why I think it's so fascinating, quantum gravity, why I like this problem in theoretical and fundamental physics particularly, and I will talk the magic of quantum gravity. So let me start from that, about the empirical inputs. And before that, this, you see, if you ask what are the approaches to quantum gravity, what people do into quantum gravity, you get different answers. And if you go on Wikipedia and look at the list of approaches to quantum gravity, you get a large number of them. Here's a few sort of arranged by connections and by areas. So it seems that at first sight that the research in quantum gravity is very much dispersed in all sorts of directions. But I think this is a false impression. That's not really the case. We do have some theories of quantum gravities, not one, because no quantum theory of quantum gravity has been sort of supported by experiments so far, but absolutely not so many. We have 1, 2, 3, maximum 4, really, if you want to be very generous, actual possible theories in the literature. A lot of the rest, it's some ideas. Quantum gravity is a fascinating topic, and it's open. So people say, well, I have this particular idea, maybe it's going to be relevant for quantum gravity in the future. So you publish a paper, a little group develop an idea for a while, for a certain number of while. But most of these are not even quantum. Sometimes are just classical hypotheses of how the world could be, no H-bar, no quantum mechanics. Sometimes based on wild speculation. So there's a lot of things going on, and I'm not saying that they are not necessarily interesting. I mean, who knows? Maybe they would get somewhere. But we have theories of quantum gravity which might be right, and which are trying to get connection with experiments. And that's a rough picture of the landscape of the various theories. And you see, in the red area where loop quantum gravity is, are theories that just take general relativity and quantum mechanics without any additional sort of strong physical input, like a violation of quantum mechanics, like violation of Lorentz invariance, like the existence of supersymmetry, high dimension, things we haven't seen yet, and so on. Then there are all around these other possibilities, and one important division in quantum gravity approaches are those on the right here, which, like in quantum field theory, assume that you can go infinitely small. There are degrees of freedom all the way to infinity, so you have the same renormalization issues as quantum field theory, and those that assume that something physically blocks the possibility of going to arbitrarily small. And both string theory and loop quantum gravity in different ways do that. All right, so let me just jump to the list of empirical results that I want to talk about. And I'm going to talk about three, which we already have, and one which is particularly excited and I think is forthcoming soon. And the first one, I think you all heard about this. This is an old paper, and just put there one of the many, many people who are, one of many, many papers that confirm this, is that contrary to what a large part of the community interested in the problem of quantum gravity expected, no supersymmetry has shown up at low energy. Okay, when the LHC in Geneva at CERN started working, a big bunch of the researchers in quantum gravity, many of them in Cambridge also, and in many other places, were sort of 99.9% sure that the LHC would have turned out on supersymmetric particles. It didn't. And nowadays, nobody's hoping that at that energy, in that regime, there are supersymmetric particles. Now, this has been called the big crisis of physics in some, there was an article in France in Le Monde, so was the title. Of course, it's not a crisis of physics, it's a crisis of a certain set of ideas of how the problem could be solved. So all this world, supersymmetry, strings, is not ruled out, the possibility, but nature has talked. Nature speaks, and I think we better listen to nature, that is a direction which is facing tension with what has been observed so far. Of course, supersymmetry might still exist at higher energies, and the previous arguments based on something called naturalness that shouldn't be there were wrong, but nature talks. Second example, there's a number of avenues for searching for a quantum theory of gravity. A lot of papers written in journals exploring the possibility that Lorentz invariance is violated. So the symmetry of special relativity, the basic symmetry of between space and time of Einstein in 1905, it's broken at very high energy or at very small distance. If it is so, in a sense, it's easier to write quantum theory of gravity. So there were theories written down. One is called Rovelli theories and others, which try to build a quantum theory of gravity by assuming that Lorentz invariance is broken. So this was very, very popular 10 years ago, and a big campaign of astrophysical observations started. And once again, this is an old paper here many years ago, but nothing has changed since. In fact, all these results are reinforced. We now have pretty strong evidence that there is no violation of Lorentz invariance in astrophysical phenomena at scales, I mean, phenomena that could be expected at scales which are compared to the Planck scale, so the quantum gravity scales, and beyond, and far beyond. So once again, nature says, no, guys, that was not the right direction if you want to solve the quantum gravity problem. And a third example, it's a cosmological constant. And this also happens, something quite remarkable, because this is the Einstein equations, which, you know, for those of you who haven't studied general relativity, is like the Maxwell equation for the electromagnetic field. These are the Einstein equation for the gravitational field. And they have a term that, in fact, Einstein added the year later. He wrote the term without cosmological term in 1915, and then a year later he added, 1 or 2 years later, he added this term with a constant, which is a cosmological constant. And for theoretical reasons, a lot of approaches to quantum gravity work and developed assuming that lambda is negative. It's a negative cosmological constant. Cosmological constant is a sort of force at very large distance, like it's a correction to the gravitational force at very, very large distance, which, depending on the sign of lambda, can be repulsive or attractive. And it only affect very, very large distances. So you see only cosmologically somehow. And lambda is positive, the expansion of the universe accelerates, and vice versa if it is negative. And even today, if you go into theoretical literature, a lot of work is done assuming that lambda is negative. Okay, everything that goes under the name ADS-CFT, duality, bulk boundary relations, ADF-CFT. ADS means anti-de Sitter, which is a solution of these equations when lambda is negative and there's no source. Except that lambda is positive. It was measured by the cosmologists. They got a Nobel Prize, here they are, and it was remeasured in a number of ways, and there's no doubt whatsoever that lambda is positive. The right equations for the gravitational field are these ones with a positive lambda. And people make a big fuss about, oh, but this is, you know, vacuum energy, dark energy, complicated things. Maybe, but as far as we know, these are the equations with a positive lambda. And this is, again, nature speaking. We didn't know, we measured, and it's like that rather than like that. And it's definitely a problem for all the research that aimed at quantum gravity, which sort of developed assuming the lambda is negative. So these are three strong cases of nature speaking. Let me mention a fourth one in a completely different direction. There is another possibility of doing quantum gravity. Let me go back to the big picture here, which is to imagine that quantum mechanics is wrong. Okay, so quantum mechanics is somehow violated because of gravity. And a beautiful idea, since this direction, Roger Penrose has written a lot of that. Roger Penrose, of course, last Nobel Prize in this in relativity, is one of the greatest mathematician and theoretical physicists in this area. And among his very, very, very many ideas, there's one that quantum mechanics can be wrong. So the Schrödinger equation is wrong. The real thing is nonlinear instead of the Schrödinger equation, and because of gravity. So if so, there isn't really a quantum theory of gravity that keeps this into account, but if so, it might be easier perhaps to make a quantum theory of gravity. Except that a lot of measurement have been done. This is just one, again, of many testing quantum mechanics. And quantum mechanics seems to be so far the most uniformly, spectacularly confirmed theory, general theory we have, and also the one of which we have no indication whatsoever where it should go wrong. And in particular, the idea that it's a gravitational phenomenon that modifies quantum mechanics. The idea was that somehow gravity creates the collapse of the wave function. What happened in a measurement is that really gravity coming in and making the measurement. And you can model that in theories, and but the experiment seems to be no so far to all these ideas. So you see, if you start throwing away the things which are not yet a theory, the things which are in tension with what nature says, nature is telling us, well, let's zoom on a few approaches to quantum gravity. And the last piece of experiment evidence that I want to talk about before going to the theory is something which, contrary to the other four I mentioned, has not been done yet. But it might be doable, and it might be doable in a certain number of years, presumably not too long. It is a recent idea, and it's an experiment that can be done in a lab. It's a laboratory experiment. It is spectacularly beautiful. People for decades sort of squeeze their minds to ask, can something quantum gravitational be measured, not astrophysically, not in the Big Bang, not in the black holes, but here in a lab? And certainly not in the big particle accelerators, because you don't have enough energy. Quantum gravity energy is much, much higher than anything you can dream of obtaining at CERN or the particle acceleration. And nobody came out with an idea, and then somehow an idea came out, and it's incredibly simple and beautiful, and it's the following. You take a particle, this blue particle, and you split a quantum particle, a nanoparticle, and now something we can do in the lab not me, I mean, so experimentalists can do in the lab, is to put the particle in a superposition of two different positions, right? You stand Gerlach and the particle is sort of half here and half here. So you have a particle in a superposition of two spots. And then you take another particle, you do the same. And then you hold the two for a little time in such a way that, this blue here, the right of blue and the left of the green are nearby. So there's a distance between the other, which is small. So you keep them small. And there's a gravitational interaction between the two. And it takes a few lines of calculation, just basic quantum mechanics, the first course of quantum mechanics, to show that because of the interaction, which is only this branch and not the other, the two particles get entangled, quantum entangled. So then on each particle you measure, I don't know, the spin, and you find that they're entangled, violate the Bell inequalities, okay? And therefore, they have been entangled by gravity, by the gravitational field. But in order to entangle them, the gravitational field must be in a quantum superposition. So if you want one particle feels a gravitational field in a superposition of two fields, and since the gravitational field is generativity in one line, the gravitational field is the geometry of space-time. Since the gravitational field is the geometry of space-time, this particle feels a superposition of two geometries of space-time. So it's really a quantum gravity experiment, even if in a lab, in a sort of non-relativistic setting, but nevertheless, it's a quantum superposition of space-times. And for doing that, you sort of should hold a nanoparticle in a split position for about a second. We're not very far. Experimentalists tell me that we're not very far. Perhaps in a few years we'll get there. I think it will be in a momentous result, because it will be an actual realization of a quantum gravity measurement in a lab, which also is nature talking, because we'll rule out another set of ideas, which have been in the literature, that you might have heard about, that perhaps gravity doesn't have to be quantized. Since gravity is space-time, maybe it's not quantum. It's different than the other forces, and is intrinsically classical. Well, if you do this experiment, if you come out right, what we expect, this is ruled out as well. So that's the situation. There are many tentative theories, but many of them are intentional with recent empirical data, many are extremely incomplete, and some are disappointing also in what you hoped to do with this theory and didn't work. So let me now, after this panoramic of experiments and theories, zoom to loop quantum gravity, which is, in my opinion, the best candidate, not the only one, but the best candidate we have for a theory of quantum gravity. What I'm going to do is to tell you roughly what it is, flash a slide with all the equations. So you see all the equations, this ones, and then talk about what one does with that, what it tells about space and time. So first of all, since I mentioned that, there's no violation of Lorentz invariance. The theory is Lorentz invariant, so it's okay with that part of experiment. There are no extra dimension, no supersymmetry. Okay to that part of what nature says, and no violation of quantum mechanics. So quantum mechanics is just quantum mechanics. And the strength of the theory, in my opinion, is that it's conservative in some sense, very conservative. Namely, the physical hypothesis is just generativity in quantum mechanics. So the idea here is there a quantum theory? Can I write a quantum theory whose classical limit is generativity? It's almost a well-posed problem, right? Mathematically. Can I write a Hilbert space set of operators and transition amplitude such that in the classical limit, I get the theory of gravity that works so well, general relativity, with black holes and gravitational waves and so on. And you probably know that the difficulty is that if you do that in the usual way in which we do quantum electromagnetism, or QD, or quantum strong interaction, it doesn't work because there are infinities that cannot be treated. You know that in quantum electromagnetism there are infinities, but there's a way of treating them and dealing with them, which is called normalization theory. It does not work in general relativity. And what happens is, and I'll explain why, what happens in in loop quantum gravity, the theory is non-perturbative. So it's not a perturbation expansion around space-time. And space-time itself is treated quantum mechanically non-perturbative. I just told you from the experiment that space-time can be a superposition of space-times. So you don't assume that there is a given space-time, and therefore you don't assume that there is infinitely small distance. And the theory itself shows that there is no infinitely small distance. Why? Well, because quantum mechanics shows you that there are gaps, there is discreteness, right? Think of the harmonic oscillator energy. You can have one energy, one energy, one energy, and that's it. There's no half the minimal energy of the harmonic oscillator. There's no state with 1/5 of h bar omega. Okay, so there's discreteness down there. And because of this discreteness, quantum discreteness, the geometry of space-time, gravity, is discrete. And because of that, there's no infinity small, and because of that, there's no infinities. Okay, historically, just to say you why loop, historically, the theory emerged because back in the 60s, I suppose most of you were not born, Bryce DeWitt and John Wheeler wrote sort of the quantum equation for quantum gravity. It's a Schrödinger equation for general relativity. There's a wave function where Q is a geometry, so it's not a variable, it's a field. And if you do a naive intuitive quantization, you get to this equation, which is badly defined. You can do anything, you cannot do anything. People work for that, but didn't go much far until in the late 80s, solutions of these equations were found, which were connected to loops. Loops here is gamma is a loop, is a closed line in space. And you can write the gravitational field, for those of you who know this mathematics, in terms of a connection, like the Maxwell potential. And the line enemy, the integral of the connection along the loop, or the holonomy of the connection along the loop, turns out to be a solution of this equation. So these strange loop states sparked a long work for sort of unraveling this equation, and quantum gravity was born. Loop quantum gravity was born. And now, which is 20, 30 years later, this is loop quantum gravity in one slide. I promise you loop quantum gravity is a slide. This is it. I'm not going to illustrate these equations in any details. In fact, I'm just saying a couple of words about that. It requires a little course in mathematics, not particularly long. There's some group theory. It's something you can learn in a couple of weeks, or not even. But it requires some steps, and of course we don't have time to go that. What I want to tell you is the structure of these things. There's a Hilbert space, because all quantum gravity is a Hilbert space. The states are in a Hilbert space. So there's a well precise definition of Hilbert space. And what is strange is that the basis of this Hilbert space, the state of the quantum gravitational field, can be labeled by what's called spin networks. Spin network is it's a mathematical thing that Roger Penrose in the UK invented long ago, back in the 60s. In the back of his mind was a quantum description of space-time. It was just pulled from there, this mathematics. So it's a combinatorial thing. I'll come back to that. And on the Hilbert space of, with this basis, there are a set of operators, which certain commutation relation with certain algebra, and then you have transition amplitudes. Okay, so those of you who know a little bit of, quantum mechanics of a particle, you have Hilbert space operators and the Hamiltonian that give you transition amplitude. In QED, you have the Hilbert space, the Fock space, the operators are creation, annihilation, and then you have the Feynman graphs to give you the transition amplitudes. And the transition amplitudes are between one of these states and another one, from a spin network to another spin network. And like in Feynman theory, Feynman graphs, you have sort of Feynman graphs that go from one spin network to another. But if you think that the dots here are the particles, this is a dot, a node of the spin network. This is a Feynman graph vertex, but there are also these links, and these links span sort of surfaces. So you construct this thing that is called spin foam. Foam, because if you think of a foam, there are little surfaces that join in edges that join in vertices. And so you label the terms of these integrals. These are integrals of SU2, SL2C groups. one can prove that this is a finite. Everything is finite here, and you compute transitional amplitude with these things. All right, so this is math. What does it mean? I mean, how is this connected to quantum gravity? Well, first of all, the way to think about these spin network states is that the nodes represent actual little quanta of space, like the photons are the quanta of light. These are the quanta of the gravitational field, and the quanta, since the gravitational field is space, this is a quanta of space. So little chunks of space, okay? And then in the theory, you can compute the geometrical aspect of this pieces of space, because the links tell you who is next to whom. So you can think like the polyhedra. They're not polyhedra because they're a quantum thing. And you can compute for each one of these the volume or the area of the faces that separate one from the other. And there's a standard calculation in quantum mechanics. You have an operator, you compute the spectrum of the operator. Then when you diagonalize the Hamiltonian of the energy, the energy of the atom or an harmonic oscillator, you get a spectrum. So you get a spectrum of the possible value of the area, for instance, or the possible value of the volume. Of what? Of anything. Just anything in space is made. The space is made by these junks, and the volume and the area are quantized in a with discrete eigenvalues. So you see, it's not possible to have arbitrary small things. There are no small things no arbitrary small things. Like the spin of a rotating particle. Study quantum mechanics, you find out that it cannot be less than h bar half. That's minimum. There's nothing is rotating slower than that. Same here. There's no space smaller than that. So this spin network, this is a basis, right? General space-time can be a superposition of these things, but it's a basis. General space-time is a superposition of things, each one of which has a discrete geometry. And this last sentence here, it's a key one. These are quantum states. But so they resemble the Fock space of QED, I mean, photons. But there's a fundamental difference here. The photons, each photon live in space-time, move in space, is somewhere. These are not somewhere, because these are space themselves. These are the where. The space is made up granularly by these things here. And then you make transitions between a spin network to another spin network, so to a space, three-dimensional space to another three-dimensional space, and you describe a process, a part of space-time, through these equations that I told you that give you transition amplitude, the probability of going from this geometry of space-time to this geometry of space-time. And the way to think about that is that, you see, in quantum mechanics, you always have an observer or an apparatus, something that measures. And so you always describe a quantum process as seen from another system. And it's called Heisenberg cat, C-U-T, not C-A-T, Schrödinger cat. The Heisenberg cat is a separation between the quantum system and the observer, which of course you can move around. It's not, your prediction depends on where you put the Heisenberg cat, but if you move out, the final prediction is the same. And in quantum gravity, the system that you're observing is a region of space-time. And the Heisenberg cat is a boundary of this region of space-time. So imagine that in this region, I don't know, there's a black hole collapsing and going through a quantum process, evaporating, and then going through a quantum gravity transition, exploding. You think of this enclosed in a space-time region, so regional space for a certain interval of time, and you compute the probability of something beginning and something after. And that's my last slide about the theory. You see the key, what's going on here. Quantum theory tells us that many variables have discrete spectra. Discreteness is the core of quantum theory. That's why we call quantum theory. Quantum because a little quanta. And general relativity tells us that geometry is the gravitational field. So geometry is a physical variable. And since it's a physical variable, it's quantum. And since it's quantum, it's discrete. So when you put them together, quantum gravity tells us that geometry is discrete. And since geometry is discrete, the infinities of quantum theory are fake, are the result of the approximation where you neglect the discreteness of space. So you see, quantum mechanics and generativity together save themselves from the disaster of quantum field theory. Good. So this is the theory. How am I doing with time? Good. I not much to talk more. I'm going to give you a couple of applications of this theory, how it's used, what people are doing with this series. Just one or two slides, no more. Just to tell you how people are trying to get empirical support for this theory. One, of course, is cosmology. Because early cosmology, the universe near the Big Bang, was definitely in a quantum gravitational situation. So you take this theory, try to apply what happened at the Big Bang. So it's, approximation work, it's a lot of papers, a lot of things, a lot of theoretical work. The bottom line, it's the core of the bottom line, because then there's much more to do. It's pretty simple. An expanding universe, this is a picture of an expanding universe, is described the scale. The scale A evolved with time, grows according to an equation in classical generativity, which is the Friedman equation. So the books is this one. So the time derivative of A over A squared is proposed to some constant, and the density of matter. Now, if you start from full quantum gravity, you do approximation, blah, 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 you don't get to this equation, but you get to a correction of this equation. The correction is this extra term here, where rho is again the density, the energy density of matter, and rho PL is rho Planck, is a Planckian density. So it's a constant. And you see, when rho approaches rho Planck, so when you go back in time, and the density goes, the universe is smaller, so the density goes up, up, up. At some point, you get to the Planck value. 1 minus 1 is 0, so this becomes 0, and the velocity A at the expansion, when you go back in time, decreases. At some point, becomes 0. And in fact, you can continue the evolution. This can be done. It's just a sketch of the calculation, but you can be done doing the actual quantum evolution of the state, and you discover that it goes to 0. And instead, if you go back in time, instead of falling into a singularity or emerging from a singularity, there is a bounce. You come back, okay? Because there's a minimum, if you want, there's a minimum dimension. You cannot squeeze things too much. I mean, there is no 0 dimension in nature. So at some point, you bounce. For a reason which essentially is the same reason for which the electron doesn't fall into the proton in an atom. I mean, why doesn't fall? Classically, it should fall, should radiate and fall. Why it doesn't? Well, because quantum mechanics, there's Heisenberg principle. You cannot squeeze things too much, right? Push plus. So the universe itself, you cannot squeeze it too much. And if you evolve back in time, there's a bounce. So the picture, I was sure, no, of course, but the picture that the theory is suggesting is that what really happened at the Big Bang, there was a collapsing universe, or a collapsing region of a universe, huge, and it bounced it up, and that's our Big Bang. Now, how can we test that? Well, by doing the physics of the bounce. It's complicated. There's inflation. There's no inflation. We don't know, all sorts of details, and trying to figure out if the bounce picture leaves some traces in the cosmic background radiation, which is observed. It's a picture of the famous cosmic background radiation. It's radiation we get from the sky, which is the oldest thing we can measure. And at large, this is an expansion in angular modes. On the left, there are the large modes, so the correlation between different regions of the sky. What happened at the bounce does affect what happens here. There's a lot of experimental observational uncertainty. It's a lot of theoretical uncertainty. The hope is that at some point, the measurements in this region of the observations of cosmic background radiation could match the prediction of the theory. We're not there yet, but the hope is there. And the other application, I just mentioned 2 applications. We got black holes. So let me just tell you why all this is relevant for black holes. Everything we see in the sky right now, black hole is classical, okay, no quantum. So this beautiful picture of black holes we have seen a couple of years ago. It was a great emotion for me. I've studied black hole all my life. Finally, I see a picture. Gravitational waves emitted from black holes, cosmology, the role of black hole in cosmology, the mysterious role of the black holes at the center of the galaxies. Did they originate the galaxy or not? What is the exact story? This is all classical generativity, no quantum. But we know that in the future, black holes are going to evaporate. This is Stephen Hawking prediction, and become smaller and smaller and smaller. This is a way. This is called a Penrose diagram or Carter-Penrose diagram. It's the structure of space-time. The gray is the star. This little line here is a black hole. This is outside. The infinite line is when you're infinite distance. So the black hole becomes smaller, 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 and then when it's very small, it becomes quantum. And people for a long time has thought that, well, maybe at that point, becomes small, 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 there's no energy, poof, disappears. So you're back to a space-time without a black hole. So the standard Minkowski space-time without a black hole. All the energy has gone out in Hawking radiation here. But that's not what loop quantum gravity suggests. Loop quantum gravity suggests is that this is a quantum gravity region. So you can do a transition to a different space-time, and you don't do a transition into nothing. You do a transition of space-time, which is like the black hole, but sort of time reversed. It's a bounce. Once again, it's a bounce. And the inside of black hole, if you time reverse it, is a white hole. So the horizon of black hole becomes an horizon of white hole, and you have this long-living, very long-living, small, because the black hole becomes small in the meanwhile, remnant of the black hole, which is out there. And so astrophysically, there might be all these remnants of ancient black holes which are out there, which predicted by the theory to be of Planckian mass. Planck mass is a microgram, it's a few micrograms, it's like my hair, a black hole with this mass, like my hair, floating around. So it's tempting to suggest that this might be dark matter. Of course, you know that dark matter is a big mystery. We don't know what they are. There are many ideas of what they could be, but among the various possibilities, we don't know. It could be that they are ancient black holes, primordial black holes, or even pre-bounce black holes that have gone through a quantum gravity transition, tunneling like standard quantum tunneling, become white hole and lived very, very long as white holes. And a white hole is just a little grain of sand which interact only gravitationally out there. Is that, are we sure? No, of course, but that's a possibility, and I find it fascinating possibility that we haven't measured anything about quantum gravity. Maybe we have. Maybe that's that matter. Just we hadn't recognized it. Remember that black holes were measured in the 30s. The radio wave from big black hole center of our galaxy was measured in the 30s. For decades, nobody knew what it was. Now we know it's a black hole. Good. So I conclude. It's quite fast, the last part. What's the beauty in my eyes of all of this? Well, the beauty is that I started off by saying that loop quantum gravity is very conservative. So just generativity and quantum mechanics, and finding a way to make them work together, and then doing standard quantum mechanical calculation in generativity, eigenvalues, transition amplitudes. I think we're doing regularly theory quantum mechanics, whether it's condensed matter, QED, quantum optics, lasers, or whatever. But once you apply quantum mechanics to space-time itself, it's obviously very radical what come out. So the hypotheses are conservative, but the outcome is very radical. So let me flash rapidly this conceptual radicality of quantum gravity very rapidly and very fast. First of all, there's no time variable in quantum gravity, right? These are the questions that I showed before. I didn't go into details, but I never told you a t variable. There's no Schrödinger equation evolution in t. There's no t here at all. So there's no time variable. What does it mean? What does it mean to have a theory without time? Doesn't mean anything so radical after all, because if you think for a moment in general relativity, classical general relativity, you don't have one time, there are many times. If you take two clocks, okay, and you throw one clock up and you catch it back, then the time lapsed between the moment in which you threw and the moment in which you get it back is different measured by the clock that went up and down, and from what is measured by the clock staying down. So which one is the true time? It's just 2 times. There's no true time here. It's absolutely meaningless. You can say, well, I like this better because that's a geodesic. Or you can say, oh, I like it better because it's static. But somebody else can say, well, I like it better because I'm in Beijing and my Beijing time is different. So it's not, there's no the time in classical general relativity. So once you go to quantum gravity, this becomes much stronger, because since you don't have a preferred time variable, you just have to deal with clocks and variables. And the theory describes how things connect to one another. The theory is predictive, but how things evolve with respect to one another, not the way they evolve with respect to preferred time variable. There is no space. In which sense there is no space? I told you that the quanta of gravity are not quanta in space. They're themselves the quanta of space. So there is space in the sense that we're talking about the gravitational field, which is a constituent, what the thing we call physical space. But we're not doing the usual story of describing how something moves in space, which is what we do in classical mechanics, electromagnetism, in quantum mechanics, in quantum field theory. We always say, well, there's space and stuff moving in space. This is completely different. This is the quantum of space itself. So quanta are not localized in space, they define themselves localization. And the classical space-time manifold that you use to do usual physics emerges in a limit in this precisely the same sense in which the electromagnetic field, continuous, classical, emerges as a limit of many photons. And this, I love this transparency, because this is how we change the basic way we think about nature since the Renaissance, okay? Newton taught us a very effective way of thinking about nature, which is there is space, time passes, and there are little particles moving around subjected to forces. Fantastic, it works very well. But Faraday and Maxwell said, wait a minute, something is missing, the fields. Okay, so the ontology of the world is more complicated. Particle, field, space, and time. And then we have special relativity, and space and time are not so separated. It's not just a single space that evolves in time. It's complicated, depending on how you look at it. So you better think in terms of space-time. So instead of space-time, it's just space-time. And then quantum mechanics comes in, and the particles, as you know, if you've done any introductory quantum field theory, are just excitations of a quantum field, right? An electron is a quantum of the Dirac quantum field. And like a photon is a quantum of the electromagnetic field. So you don't have particles and fields in modern physics, there's just quantum fields. And general relativity tells us that space-time is a field, okay? Because space-time is the gravitational field. That's the core of general relativity. Now, if you put everything together, you have a single entity, which is a covariant quantum fields, whose quanta are the grain of space, the photons, the protons, the neutrinos, they're all on the same ground, so to say, and they don't live somewhere, they live on top of each other. And the structure of their being together is space-time and the world that we describe. Very rapidly, in quantum field theory, you look at from infinity. You don't need to do that in quantum gravity because the transition are local. You describe, if you want to describe how a black hole evolves, tunnels from a black hole to a white hole, you just encapsulate the quantum region in a box, and you compute that transition. And you can say, this is maybe a bit provocative, that we're not talking about things, we're talking about processes. We're talking about what happen in space-time regions, given something I measure first to something I measure last. And who is a measurer? Let me make one step in between. Because of what I said, these processes, okay, that we compute are not processes happening in space-time, they're the processes of space-time itself. The transition amplitude from one spin network to another is not something that happens in space-time, it's the evolution of space-time itself. And who is the observer? Well, the observer is not outside of that. The observer is just a part of the universe that we're looking at another part of the universe. So if this quantum region, I can compute its probability transition with respect to an observer, the observer itself might be in a quantum region that, with respect to a further observer, I can compute its own probabilities. And finally, as I said, we already have Planck scale measurements. For instance, the non-breaking Lorentz invariance that astrophysicists checked, it's a Planck scale measurement. We already have a large number of hints from nature, supersymmetry, positive cosmological constant, no breaking Lorentz invariance, and other, favoring some theory, disfavoring some theory. And perhaps, this is very speculative, we may have even observed something already, which is dark matter. We don't know, but it might be. That would be great. So these are the 9, whatever they are, I'm not sure of the number, aspects of the radicality of the theory that emerged from this conservative idea of just doing quantum mechanics for general relativity. No time, no space, no asymptotic infinity, events, processes, not things which are not happening in space-time, but they are designed the space-time itself, no external observer, and perhaps even already measure things. And I close with my last slide, which says that I think you get from my tone and the way presented, I think the key fact for me about quantum gravity, it is a horrendously charming theory. Thank you.